Again, good morning and welcome to this class. Today is May 3rd, and I'm hoping that some of you have already applied for this grant consortium for the NASA, basically between UCSD and NASA. Anyway, today is a very important topic that we need to it's going to have implication on the exam. So I'm hoping that you guys focus on this stuff today, more so than the first one. The first one was actually the first chapter of optics was a little bit easy. So this one we're getting a little bit into more geometrical optics. I know some of you already have had this topic before in the past, namely when probably you did it in high school or intro physics or something like that. So even this topic should not really be hard enough because it's really geometry. As a matter of fact, I'm going to recommend, let me look at the book in here, that you focus on the construction, geometrical construction of this shapes. So, and one of them involving lenses, and that's page 1132. So page 1132 is a very important page. Let me share the screen. Oh, okay, I'll share the screen quickly, okay? But I'm gonna write it down in here anyway. So page, so this is for lenses. And also the other page that I want to bring your attention to, I think page 1122, 10 pages earlier, that is for the mirrors. Albeit all of these mirrors that you have in here are convex mirrors, or concave mirrors, but it should not be hard to do the convex if you know how to do the concave. Yeah, so the other one is 1122, and this is for concave mirrors. Okay, so again, we're going to get into geometrical optics. The main law that we're going to see is how it connects the position of the image if we know the position of the object. And there is a basic relationship that you're going to see it time and time again, repeated, namely the inverse of the position of the object plus the inverse of the position of the image is equal to the inverse of the focal point of the device. So if it's a mirror, it's the focal length of the mirror. If it's a lens, it's the focal length of the mirror. Choosing that focal length, though, is really sometimes can be tricky because if it's a lens, and if you're trying to build a lens, trying to find these focal points, you really have to know how to do it. If you're trying to build a mirror, first of all, if it's a flat mirror, its focal length is infinity, so you don't worry about it because there is no curvature for it. But if it's a mirror that is concave, cave is when you go into it, so you can think of it that this is a concave, then in this case, it depends on the curvature. The more curved the mirror, the more concave it is, so the focal length is smaller. But if you open it more and more, then the focal length will become further and further away. It focuses the rays very far away from it. If you take that mirror and instead of shading it this way, so that it's reflective on this side, you shade it actually from this side, and you make the reflective side on this one, this side. So the same mirror that you have built for being concave, you can make it into a convex mirror by shading the other side, basically. And now this side becomes the reflective. So this is in a nutshell an intro to the topic. So let me share with you the screen. So we're doing chapter 34. So let me share with you the screen so that we see exactly what we're talking about. So as I was saying, it is very important that you guys look at these two pages, okay? Page 1132 and page 1122. It gives you how you make graphically an image out of an object. So you have an object. The purpose is to see where the image is formed, okay, and how big it is, okay? And that is why this topic today is actually the subject of chapter 34 is all about image formation. What you want to know is the following. This is the fundamental question you're asking, really. First of all, if I know where the object is, I want to know where the image is. Okay? The second thing is, if I know what the height of the object is, I would want to know the height of the image. In other words, what I want to know actually is the magnification of the device. Had the image amplified? You started with a small object and now the image of the object is bigger. Or has the image shrunk, okay? Or stayed the same thing. So that is the magnification. So we would want to know that. The other thing also is, which is very important, is the image upright or inverted? Inverted versus upright. In the textbook, and almost in every textbook, they use the word erect. Okay? So an upright image is just like the object. So if the object, if you stand in front of the mirror, when you look at the image that is formed on the other side, you look like the image has the same standing. In other words, it's not flipped. So in this case, I would say that the image is actually upright. Okay? Whereas in other devices, for example, and their lenses and some other devices, the image could be inverted. Okay? Do I have any lenses in here? Sometimes they do, sometimes they lose them. I'll try to do a demo in here. I don't have any. Oh, here is a lens. Actually, this lens is a concave lens. It's not the standard lens that you guys are basically probably look at the image in here. And at some point, yeah, that's basically how the image forms from it. So again, this is the pen. But then it could be reflecting on other devices, and then you have that. I have other lenses, but I don't know what they are right now. Anyway, you get them in packages from Amazon, and I basically disperse them after I demo some of them here and there. Anyway, so that's another question you would want to ask: is the image inverted or upright? The last question that usually we ask about this one in here is the image real or virtual? Let me give a simple explanation of what real and virtual is. When you stand in front of the mirror, that image is not real. In other words, there is no, if you take a film, for example, and put it on the other side, because that's where the image appears to be coming from. It appears to be coming from the other side of the mirror. And you put that film out on the other side of the mirror, and you expose the film. Nothing is going to develop because there are no rays going into it. Okay? So in this case, I say the image is virtual because I cannot really make out of it an image. Okay, I cannot produce a real image out of it. But there are some lenses, for example, and some mirrors that the image is going to be real. So those are the four questions that we usually are asking is, where is the image? How high is the image? In other words, what is the magnification of the optical device? And the third one is the image upright or inverted? And the fourth one and the final one, is the image real or virtual? So those are the questions that we need to ask, okay? So, as I was saying in the beginning, there are two basic devices that we're going to be dealing with. There is the image, there are mirrors, and then there are the lenses, okay? One of them uses reflection. The mirror uses reflection, a reflective device. whereas a lens uses actually refraction. So we're going to come to later on to lenses, okay? Lenses use refraction. That's the only difference between the two, okay? Because there are two Snell's laws. So assume with me that we have this mirror. It's shaded on this side, meaning that when rays come from this side, they're going to bounce off. They're going to reflect on this side. So this is a concave mirror. It's very hard to build one. I mean, okay. And I would want an object to be somewhere in here. Okay, on this side. Of course, it has to be on this side. So the object is on this side, and I'm asking the 4 questions. Where is the image? How high is the image, or the magnification of this mirror? Or and then also, is the image upright or inverted? And is the image real or virtual? So I'm going to ask all of these questions and see how we're going to answer that. So this is the example that we're going to focus on, and it's a concave mirror, okay? Before I do that, let me introduce the concept of focalization, how to focus rays. So what I'm going to do in here, I'm going to show what shape we really need to do in order to have a ray, a device that focuses all the rays. So what I'm going to say in here, I'm going to create this shape. Oh man, terrible. Okay, let me do it as I did before, and then come to the okay, I'm going to just show the condition under which a mirror is formed in here. So I'm trying to erase this, because this is actually a sphere. And it's not going to work as a focusing device. So what I'm saying is the following. So let me draw a line now. Okay. So this is a device, the one that I was describing earlier, that I want all the rays coming from infinity to focus on one point. Okay. So basically what I'm saying in here, this device could be useful, for example, for studying stars or very far away objects, okay? So I want to know what shape do I need to make it, okay? Obviously, it may look like this one, so that the rays, they're coming from here. Let me draw the rays. So this ray is coming from infinity. Oops, Control Z. And then once it hits there, Snell's law still apply, in a sense that the normal to the surface, remember the normal to the surface is tangent to the surface. So if I draw the tangent to this surface in that point, and draw now the ray needs to bounce off and it's going to come out this way. Probably, okay, something like this, okay? Obviously, a ray that comes in from here comes in on the exact axis in here of symmetry, which I drew in here, is going to hit the mirror in this point. But because the normal in here is actually the y-axis, the way I'm representing this one, when it's going to bounce off, it's going to bounce off again on the same axis. So it's going to come out here. Since I drew 2 rays, that's all I need, really. So this is the focal point. I know 2 lines meet in the same point. Now, if I draw any other ray, it doesn't matter where. As long as it's coming from infinity, it should do the same thing. So if I draw It's much easier actually to draw it backward than to draw it. So if I'm here, for example, I can say that it's going to also focus because it came this way. Okay, it came here. Okay, probably. Okay. So the same point, any ray that comes in from infinity will focus on the same point. That is the condition I'm trying to say here. Okay. This, by definition, is f, this distance between the focal point and the center of symmetry in here, which is going to be I'm going to call it C, and no, C is for the center, so probably I'm going to call it temporarily O, because I don't like the word O either, because usually that refers to the object, okay? And this is the focal point F. This distance is by definition F, okay? This distance by definition is F. So if the device was not there, if this device was not there, if the mirror was not there, if there were no mirror to begin with, what's going to happen in this case? This ray, I'm going to label rays now. This is ray number 1, this is ray number 2, and this is ray number 3. They will all continue moving in that direction. And they come from infinity parallel, so they stay parallel with one another. So technically, if I did not have that, this ray will continue from this point on, this far, okay? This ray will do the same thing. Will continue from this point and go unimpeded. The only reason why they're reflected to begin with is because of the presence of that mirror. So this ray now is going to continue in this direction and so on and so forth, all of them parallel, okay? However, in the time that this one travels this distance F backward, it could have traveled the same distance F here, okay? This one must have also come to the same points because they are parallel, they come from infinity parallel, so they need to stay parallel. So technically, I could have said that they will meet in this point in here, and this line in here. Okay? So what I'm saying in here is because this one bounces off and goes back to the distance F, which is the focal distance for this device, when it's present. If it were not present, at the time when it was going to bounce off to the focal point, it could have reached this point, okay? In the same time, this ray that bounced off of this point and one traveled this whole distance in here must have traveled this distance if the device was not there, if this mirror was not there. The same thing, this ray that came from infinity parallel to the other two and bounced off on this distance in here, and if the mirror was not there, it could have traveled this whole distance. So this one could have traveled that distance, whereas this one traveled that distance, and so on and so forth. So what I'm trying to say in here is the following. For the ray to work basically because again, I'm going to go back to the least time principle in here. The least time meaning the least distance in here. Because in the case of reflection, the material does not change the index of refraction. So the distance traveled is, the time taken to travel a distance is the same as the distance. The reason why is because the speed of light is the same in all of the media. So this distance and this distance must be the same distances because in the presence of the ray or not, the rays were parallel. And since this one decides to come back to this point, in that amount of time, the other one must have traveled that whole distance also in the same amount of time. So this distance and this distance must be identical because in the same time, if this device was not there, it would travel this longer distance and reach this point, which is the same distance traveled for ray 1, ray 2, and ray 3. So ray 1 and ray 2, let's say, for example, they started from this point and traveled this whole distance, which must be the same distance as this one, whereas this one reflected back a distance F, this one reflected this whole distance, which means they traveled this whole distance, this distance, and this distance must be the same, okay? So that is really the condition of focalization, that this distance is regardless of where the ray hits, it's the same distance it would travel to this axis. So this device is the following then, in order to focus rays, must have the property that all of the distances from it are the same to a point as they are to an axis. So the properties of this device are all distances from the focal point are the same as those to an axis, regardless of where you are on the point, okay? So what I'm going to say is the following. I'm going to take this point in here, P, and I'm going to give it coordinates X from O, and I'm going to give it the coordinate Y from O. So this distance is Y, and this distance is X. This distance is Y, and this distance is X. And I'm going to find the relationship between Y and X. By the way, I mean, if I didn't do that, and if you guys have had conic shapes, you recognize immediately that this is a parabola. This is the definition of what a parabola is. Parabola, okay? So that's exactly the shape that we're getting into in here. All we're going to show right now is that this shape must be a parabola, hence the parabolic antenna that you hear of, or dishes, how they are called, because they focus all the rays to a device usually called the LMB, where you can see them on top of the roofs of people who have them, and they are used for receiving signal, and actually used also for antennas outside, including the Hubble telescope and any telescope in that shape. So you would want the same behavior. You would want all the rays to come to a point, you collect that ray, the rays, and then you use them to analyze them or study them or take images or whatever you want to do with them, or convert them to a signal, for example, for your TV or things like that. So this is really the purpose of that device that I'm talking about in here. So we're going to show what is the relationship between Y, which is the coordinates of this point in space, Y and X. So I want to find how Y and X are related for this point on the device itself, okay? So for that, I'm requiring that this distance must be equal to that distance, knowing this whole distance is F actually. So if I look at this right angle triangle, this one, this is the hypotenuse whose base is F minus X and height is Y. This must be equal to this distance, and this distance is clearly F, which is this much, plus X. So that's all the requirements I'm going to say in here, that the hypotenuse of that triangle, which is square root of Y squared plus F minus X squared, which is in this right angle triangle. This distance is F from O to the focal point is F. And I took the point of coordinate X. So this distance must be X. So just this triangle in here, the side of it is F minus X, little f minus X. And the height in here is clearly Y. That's the coordinate of the point P. So this distance traveled in here must be square root of F minus X squared plus Y squared. This must be equal to, that's by definition of this device, to this whole distance. And this distance is clearly from this geometry, F plus X, okay? So this must be equal to F plus X. And I'm going to square both sides and find the condition basically on how Y and X are related, okay? So if I square both sides, this just gives me Y squared plus the square of this difference, which is F squared plus X squared minus 2FX is equal to this whole thing squared now. When you square this side, you square the other side too. So now this will be F squared plus X squared plus 2FX. Obviously the X squared and the X squared cancel, the F squared and the F squared cancel. And I have a relationship when I take the 2F with the negative sign to the other side, it's gonna be positive. And I already have positive 2 of that, so it's gonna be 4 of that. So the equation that needs to be satisfied, the way that I want to make this shape, has to be in such a way, I'm sorry, that this condition is met. And that is the equation of a parabola, as I said before. So it has to be a parabolic shape, and this is how you're going to make it. So if you make this device in such a way that it's a parabola, that any point in here, y and x are related by this relationship, where f now is going to be the focal point. Okay? So if you make it, I don't know, 0.237, divide that 0.237 by 4 times x, that's going to be your focal distance, okay? So no matter which shape you're going to do, you can build this device. And this is basically what you need to do. So if you want to build a device that focuses perfectly, rays from infinity, this is the device that you're going to use, okay? It has to have the condition that y squared is 4fx, okay? Note that x usually is small and y is an order of magnitude higher than x, okay? Because it's y squared fx. So that is really how you're going to make this one. Obviously, this is hard usually, and it's very expensive to build these devices in here. So your dish company does not really do that, okay? So what they do instead, they take exactly what I did to begin with. I don't know if you notice or not. They take a sphere, not a circle. They take a sphere and they actually cut it into the shape of a parabola, okay, and make it work. So this is what they do. This is actually, I'm trying to draw a sphere, but of course I cannot draw a sphere on a flat screen. So this is actually a cut from that sphere, okay? Think of it as this is a 3D object, okay? So what they do in this case, they say, you know what? That's fine. This is a sphere of radius r. This is the origin of the axis. This is the x-axis. This is the y-axis. Okay? And this is the center of the sphere. The center of the sphere in this case has coordinates r and 0. Okay? And they want to make a cut of it, just like I did, actually in the construction of this one, so that this will behave like a parabola. So everything else is neglected. Okay? So they want to make a condition, when can I build that? When can I be happy with it? Because it's much easier to build a sphere, okay? You build a sphere out of a metal, a hollow sphere, okay? And then usually it has to be for example, silver or whatever, and then you do coating on the other side, and then the rays now they're going to focus and bounce back into a single point, and then you can use that for your telecommunication, okay? At least for industrial applications. For scientific applications, for example, for the Hubble telescope, this is no good. You really have to spend a lot of money and effort to build this shape, okay? So this is for application. You call this one a spherical application, a spherical approximation. So what you're saying in here is that when is a sphere good enough for me? Obviously, you can cut more of it. You can cut in here too. You can cut in here too, and potentially in here too. And maybe you can come up with 4 or 5, depending on the size that you're looking for. Okay? So you can make a lot of it just from one sphere. Okay? So the equation of the sphere, if you guys remember from your geometry class, is in here, because this is an off-center. This is not centered around the origin in here. So this is centered at RO. So again, it's the x coordinates squared, but the x coordinates now is shifted by the value of r, plus the y coordinates, which is not shifted because the y-axis has the 0 axis, by symmetry it's the same point, is equal to the radius squared. So the radius of the sphere is actually r. Okay? So you say, how can I make this equation look like this one? So this is what you do. You square both sides of the equation. I mean, they're already squared, so all you have to do is develop this square. So I have an x squared minus 2rx plus y squared equal plus r squared. I'm sorry, there is an r squared from here, is equal to r squared. Obviously, the r squared and the r squared cancel. And this equation look like, so I'm going to leave y squared on this side. I'm going to move this to the other side, 2rx plus x squared. This is almost like this equation, except I have an additional term in here, minus, not plus, I'm sorry. This is minus, not plus. But when I move it to the other side, it's has a minus sign in it. It doesn't matter. So what I'm saying in here is take 2Rx as a common factor, and it's going to be 1 minus x over 2R. If this number is small enough, namely if x is very small compared to 2R, not R, compared to 2R. In other words, when you're trying to make the cut, okay, this distance better be negligible in front of the entire diameter. If that's the case, you have yourself a good enough parabola, good enough focusing device. So this is really the issue then. If you do that, then the equation, because this term will be ignored, and then in front of 1, and the equation becomes y squared is equal to 2Rx, where all you have to do now is match this one with 4Fx and say that F or 2F must be equal to R. In other words, the focal distance is half midway of a radius, okay? So this is the focal distance. This is F for this device, okay? It's midway. It's equal to R over 2, okay? If you make that approximation, you're in good shape, you're okay. So you don't really need to go through the expense of building an actual parabola, which is very, very expensive. Then you can build yourself basically a sphere, okay? Knowing upfront how much your focal point need to be. So if you bring a sphere that is 1 meter in diameter, that means R is 50 centimeters, the maximum you're going to get of a focal point is 25 centimeters, okay? And so on and so forth. So if you make it 10 meters, which is a big sphere, and you still would want only 25 centimeter spheres, focal points, then you can make so many of them. Or if you want to, you can make 50 centimeters or even up to 2.5 meters basically of focal points, okay? So the focal point is in here. The cut is still somewhere in here. It's not 25 centimeters, you cut it down. You cut it much smaller than that, okay? So you can make yourself different shapes in here. As long as you're happy with this approximation, as long as you say, you know what, I'm at a distance, for example, I don't know, from 1 meter, for example, I'm at 10 centimeters at most, okay? So if you make a 10 centimeter cut in here, the focal length is 25 centimeters. So this is how the mirror works in it. So this whole thing is called spherical approximation. As long as you're aware of it, then you can build yourself this device within here. So this device will focus the rays, and you should be happy with it, and you should be fine with it. Does this whole analysis make sense to you guys? Did you deal with the conic shapes before in your classes in math or calculus or something? Anybody? Probably are familiar with circle, which is a conic shape. You may be also familiar with the, I think the parabola also is something that you guys dealt with as basically the basic shape actually for, usually you write it backward, you write y equals to something times x squared, okay? But because I have it tilted this way, not on the y-axis, because usually the rays come this way, so that's why we have it actually x equals to something times y squared, or 1 over 4f times y squared. So that is a parabola. A hyperbola is not going to be used for device in here. The other one probably that is actually the perfect focusing device is that has 2 focal points is the ellipse, okay? Are you familiar with these shapes, guys? From your calc class or something else? Yes? Maybe? Or not at all? Okay, very good. Very good. Honestly, we're not going to do a lot of these things with this equation. Okay, so we're just basically just setting up in terms of engineering what needs to be done. Okay, in terms of basically, if you're going to build one, this is what you need to do. Okay, so let me share the screen and go back, because we're again focused on the image formation, so we're not really focused on this questions as much. So again, I'm going to go back in here. Can I erase everything in here without erasing that shape in here? Oh man. Okay, I'm going to rebuild it again. Okay, so, oh, I think I did not really mess up the original one. Good. Okay, so we still have it. Good. So imagine now we have a focal, we have a device that has a focal point somewhere in here. So this device in here has this focal point in here. So this is my F. Okay. This is the focal point. Usually I really don't label the focal point. I label the focal distance, F. Okay. So if I come in here, this is roughly twice F. So if I come in here and place an object from the origin, so this is always your starting point, okay? So the object is located at some distance S. Now I have to be careful with the symbols. This is F. In some literature, they don't use the letter S, they use the letter P for the object. In some other literature, they use the letter U for the object. So the object, so that's when you're reading, we're going to use the symbol S in this book, okay? The image, we use the letter S prime for its location. In some other books, you will find it Q for its location. And this will be V for its location. So don't be confused with the symbols, it's just symbols, okay? So I have an object in here, and I'm going to draw this object. Let me give it a size in here, okay? That's too big, probably. That's too big. Let's make it just this big, okay? So here is my object. It has a certain height, okay? So this is my real object, something standing in there, and I would want to see where the image is going to form in here, okay? So because I know that this is the focal point, any ray passing through the focal point must come parallel to it, to this axis. So this is the axis of symmetry. I need to go back into the... Okay. Any ray that comes in parallel to this one need to come out also. So let me choose colors now because it's comes in handy, colors. So a ray that comes in parallel to the x-axis, like this ray, okay, and tip the head, hit the tip of the object right on the head of it, okay? It's going to bounce off because it came parallel to the axis of symmetry. So it's going to pass through when it comes off through the focal point. So when it bounces off, it's going to bounce off. Remember, Snell's law in here, the law of reflection is the one that is giving us all of these things. So there is a normal in here. And if I apply the normal, the angle of incidence is equal to the angle of reflection. And the angle of reflection now needs to be this angle. So it's going to pass through this point in here, and it's going to bounce back into infinity, okay? So this is a ray that comes in parallel to this shape in here, okay? Obviously, the image is somewhere in here. It could be upright here, or it could be inverted in here, okay? Because I know the bottom of this object is somewhere on this axis. So where the bottom in here of the object and the top of the object is somewhere in here, okay? This is the image that formed off of it, okay? Let me draw another ray that I know how to draw also. I need to draw a ray that is going to come from, so I'm going to change the color to green. And I'm going to draw a ray that passes by this point, okay? So I'm going to drop the arrows because I know that they're coming from infinity. Besides, there is another rule for the least time. The least time doesn't care which way the ray starts from. If the ray came from this side and went through the focal point, it must come out parallel this direction. So it doesn't matter really which ways they come in. So the fact that I put an arrow in there may give you the impression that the light is coming, has to be this way. But if the light came this way, it doesn't matter. So it's going to tip the object on the other side, and that's it. Okay? Because the least time doesn't care which way the ray is coming. The least time is the least time. So again, so I'm going to draw a ray that is going through the tip. Now, if this ray comes in here, this is the normal to the surface. So this angle in here, because that is actually the axis of symmetry, and this is perpendicular to the axis of symmetry, therefore this is actually the incidence. So the angle of incidence is exactly this angle. This angle must then be the same angle of the reflected ray. So I'm going to draw the ray in here. And I have to be careful to choose the angle to be the same. Now, if this ray were to come from infinity, this is how it's pointing, and it's going to go to the infinity, this is how it's going to point. Obviously, now I have made 2 points, 2 rays, 2 different rays going through the top of the object. And where they meet, they give me the best location for the image, actually the location of the image. So now I know, for a matter of fact, not if or anything else, where the image is located. So this is where the image is actually located. There it is. Then, can I get back into my colors? Then, this is the position of S prime. That is where the image is located. Is the image inverted or upright? What do you guys think? Compared to the object. Is it inverted or upright? Come on, guys. Is the image, that's my question. Remember, we found the location of the image. We found S prime, basically, using geometry only. So we have to actually find the algebra for it. But my question for you guys is the image upright or inverted? I have to really stop sharing in order to know exactly what you're chatting, but I need to hear somebody in here. You don't have to be shy about it. There are only 2 choices.
Would it be upright?
Okay, upright meaning that it's in the same direction as the object. The object is pointing up.
Oh, and it would be inverted then, no?
Yeah, it's going to be inverted. It's important that everybody pay attention to this point, because this would be a typical question that you're going to be asked for during the problems. And that is the image inverted or upright? I mean, from the construction, it looks like if the object is pointing upward, the image is pointing downward. So this is an inverted image, okay? It looks like also it's shrunk in size, okay? Its size is smaller. So the magnification is less than 1 now, okay? And is this a real image or an inverted image? If I put a film in here, it's going to develop actually. So this is actually a real image. Had the image been formed on the other side of the mirror, just like when you stand in front of the mirror, the image is forming on the other side, flat mirror that is, then you say in that case, the image is virtual. So to answer the question, we found geometrically where S prime is, okay? We're gonna find an algebraic equation for it. I mean, an algebraic equation for it, okay? And we also found the fact that this image is inverted, and we found that the image is actually real, and the image has a magnification less than 1. just by looking at the geometry. So let's work out now the algebra so that we know how to solve these problems. So I'm going to draw a pen, which color it is. Let me get this gray color, okay? Just one more ray in here. I know I have too many of them, but let me draw this ray now that I know, as I was saying before, the ray that passes through the focal points need to come out straight out in here. So probably it will not, because again, the angles I chose maybe not exactly the right angles. Namely, I probably have made a mistake somewhere. So again, very close from where it needs to be. Okay. So assuming these 3 points are the same points, okay? Again, this is because I'm not using protractors or anything like that, okay? So let me Control Z. Maybe you can draw at least, say. Okay, close enough. I'm going to call the height of this object H. Control Z. Let me use the proper color for this. I'm going to call the height of this object H. The image's height is H prime. Okay. I know the book uses Y prime and Y, but that's confusing a little bit because usually Y has to do with the coordinates on this point in here. So I'm not going to stick with that. I'm going to use for the object the height H and the image height H prime. Okay. And I'm going to look at this angle in here. And this angle. They must be the same angle because both of them are coming off the same parallels. Okay. So I'm going to call this angle, it doesn't matter what I call it, I'm going to call it alpha. So this angle also is alpha. Also, I'm going to call this angle beta. And this angle also beta. Okay. If you're not following, if you're not doing this construction at home, you're going to have difficulty understanding where these things are coming from. So you really have to have protractor and hopefully colors also. This is the time when colors are actually needed, not an option, okay? And this is actually, you have to really be careful, far more careful than what I'm doing in here because I'm really drawing what I think is are parallels, but they may not be exactly parallels. So you have to be careful with this thing. Anyway, if you're wondering what happened in here, why do I have a cut? Remember, the whole thing was actually a big sphere that I cut part of it. So this is the cut of the sphere that I had in there. Okay, actually, it's a white color. That's why it looks like it's cut. So I'm going to say, what is tangent of alpha? So I'm going to remove this S prime in here. This is one of them. Oops, we cannot get that to get out. Can I see what is this usefulness for this thing in here? Okay, it's not used. Okay. So let me remove S prime in there because S prime actually from here, because it's getting a little bit in the way, that's all. So this coordinate now is S prime. So what I'm going to say, I'm going to calculate tangent of alpha. Tangent of alpha in this right angle triangle is equal to H over this distance. And this distance from here to here is F. And from here to here is S. From the origin to this object is S. So this distance only is S minus F. So this distance is S minus F. And this distance is H. And I'm going to say that it's equal to the tangent of this alpha. And the tangent of this alpha is equal to this height, which is actually H prime, divided by this distance from here to here, which is F. So what I know from this equation in here for the tangent of beta is the following. Tangent of beta, on one side, it's equal to the opposite of the angle beta. And the opposite of the angle beta is exactly H. So I'm going to put H over the adjacent to the angle alpha, to the angle beta. And the adjacent to the angle beta, beta, yes, is this whole distance from the origin to where the object is, and that is exactly S, minus this distance from the origin to the focal points, and that is F. So it's S minus F. So it's equal to H over S minus F. On the other side, it's equal to the height of the image, h prime, because this distance is h prime, divided by the adjacent, and the adjacent is exactly f. So it's h prime over f. That is how one relationship, if you wish. So I'm going to call this equation 1. So beta is really not a needed angle. It's just going to give me that relationship between S, F, and H prime. So I'm going to look at alpha now, the angle alpha. Oh man, I'm sorry. This is angle alpha, the one I was doing. Man, you guys need to correct me. This is alpha all along, the one whose opposite is H and adjacent is S minus F. And this is also the same alpha. So this is actually tangent of alpha. I'm sorry about that. You guys need to correct me on these things, okay? Now I do beta, the other angle, okay? Because they are auxiliary angles, we really don't need them. So it's not really necessary to even remember who they are, as long as you know that the ratio of these two sides in here, the opposite of this angle to the adjacent of that same angle, is the same as the opposite to this angle divided by the adjacent of that angle, because both angles are the same, okay? Now I do beta, this angle, okay? On one side, the tangent of beta is equal to this whole thing, which is just h over f. And the other side, because this distance is f and this distance is h. So in this right angle triangle, this is the adjacent to beta, and this is the opposite to beta. And this is actually h, and this is f. So it's h over f. On the other side, it's this side only, which is the whole s prime from the origin to here minus f. And that is the adjacent to beta, and the opposite is just h prime. So again, tangent of beta now, on one side, it's h over f. On the other side, it's h prime over s prime minus f. If I'm careful with the geometry, I'm going to make sure that this equation and that equation are satisfied in the same time. So what we have in here, let's look at these equations in here. We have on one side, h over s minus f, that's equation 1. H over s minus f is equal to h prime over f. And the second equation can be written as basically h prime over s minus f is equal to h over f. Okay, so we have a close enough basically relationships that we can solve for h and h prime. As a matter of fact, the first equation give me h prime over h equals to f over s minus f. And the second equation gives me h prime over h. This is s prime. It's this s prime. H prime over s prime minus f. So this is the second equation. So on the second side, h prime over h is going to be s prime minus f over f. So it's the same ratio, okay? This is the ratio of how high one object is versus the other one. This is, if you wish, has to do with the magnification. It's the ratio of the heights, okay? So we found actually another thing in here, except that we're going to define it better, okay? So we solve this equation now by multiplying side by side. So multiply the numerator by denominator and numerator by denominator. So we'll find in here f squared is equal to s minus f times s prime minus f. So if I develop this product in here, I'm going to get s prime minus sf minus s prime f plus, because minus times minus, that's plus f squared. Cancel the f squared on both sides, and I will get 0 in here. Move everything that is negative to the other side. And leave that one to this side. So what I have in here in this case is sf plus s prime f is equal to ss prime. What I do in this situation, this is every person who reaches this point, they do this operation. Divide by the product of s prime f. So if I do that, I have an sf that will cancel this sf, and I will be left with 1 over s prime in here. Plus s prime f will cancel this s prime f, and I will be left with 1 over s. And I have an ss prime will cancel this ss prime, and it will be left with 1 over n. This is the equation that you will need for almost every device in here. It relates the focal point to the object to the image. So if I know the focal points, and if I know where the object is, then I can tell you where the image is exactly. So using just that algebra, I didn't have to do this construction, okay? If you tell me F is 25 centimeters, for example, and the object is 75 centimeters, then I can tell you where the image is. No problem. If S is 75 centimeters, by the way, stick use with the centimeters, don't have to convert anything to anything, okay? And F is, let's say, for example, 25 centimeters, then I know that 1 over S prime is equal to 1 over 25 minus 1 over 75, common denominator, and do the algebra after that. It doesn't matter. So it's going to be what, 25, 75, and in here it's going to be 50. That's 1 over S prime. That means S prime is going to be the product of the two divided by 50. So S prime is going to be 25 times 75 divided by 50. So in here, 5 times 7.5, and 5 times 7.5 is what? 5 times 5 is 35 plus 2.5. That's 37.5 centimeters, okay? So if the object is sitting at 75 centimeter, from a mirror, the focal point is 25 centimeters, the image is going to be at 37.5 centimeter, okay? That's easy enough to do, okay? So I can do this algebra. This is easy enough. Actually, this is, it should be easy enough for a calc-based course that you can use. But this is the derivation for it, okay? This is for a concave mirror. For a convex mirror, everything is the same except that F is negative. For a convex mirror, F is negative, that's all, okay? So basically what happened then is you will have 1 over S prime plus 1 over S is equal to 1 over F. This is negative. This whole thing is less than 0 because this number is negative. And when you put 1 over S to the other side, 1 over S prime is going to be basically 1 over F minus 1 over S. So it's definitely negative. Because this is negative. So basically here is a concave mirror. You put an object in here, and you're trying to form an image in here. The focal point is somewhere in here. So when you're trying to build an image, the image is going to be reflected. And again, it appears though, so this is the actual ray, it's going this way, okay? Again, you're going to go through this point in here and it's going to be this way. So when you meet the 2 points, image is going to be somewhere in here, okay? Depending on what it is, of course, depending on where the focal point is and so on and so forth. The point being in here is the image is going to be on the other side, just like a flat screen mirror. So this image is going to be virtual. Okay, virtual. Whereas in this case, whether or not it's going to be virtual depends on S prime. If S prime is positive, that means it's going to be in front of the mirror. That means it's going to be real. If S prime is negative, then it could form in this side. So let's look at the different scenarios. How are we doing on time? We still have quite a few time to. Okay. So let's look at the different positions of the object. I took an example in purpose this way when I put the numbers. I took the focal point to be 25 centimeters, and I made sure the object is at least 2 times more than it's more than 50 centimeters away. So if it's more than 50 centimeters, I know the image is between slightly more than the focal point, but less than 50 centimeters. So I know that result. So here is the deal now. We have an object in here. So I'm going to draw just so this is the focal point. This is the twice the focal point. And this is an object that sits outside. And this is where the mirror is. This is where the origin is. Okay. If, like I did the example, the object is in here somewhere, okay? The image is going to be here, between this region only. If the object is here, moves away, so this is option 1, the image is probably here 1, okay? Option 2, if you move further away from the mirror, the image gets closer to the focal points, okay? Because this is the one where all the rays that come very far away will focus. So if the image is actually at infinity, far away, I mean, if the object is at infinity, I'm sorry, the image is sitting right here, okay, on the focal point itself, or very close from it, on this side. Now, if you bring the object closer to 2f, the image gets closer to 2f, as a 2f exactly. So when s is equal to 2f, so let's see what the algebra tells me. 1 over s prime over 1 over 2f. Remember, I put s equals to 2f is equal to 1 over f. So that means that 1 over s prime is equal to 1 over f minus 1 over 2f. The common denominator is 2f, and the numerator is 2f minus, I'm sorry, it's 2 minus 1. And 2 minus 1 is just 1 because the common denominator is 2f. So in here I have to multiply by 2, and here I have to multiply by 1. So this is going to be also 1 over 2f. That means that s prime is equal to 2f. In other words, if the object is sitting at twice, in my example, for example, the focal point is 25 centimeters. If I put the object exactly at 50 centimeters away, then the image actually is going to be at 50 centimeters, okay? So, in other words, if I put the object right, what is my picture? Right here, its image is going to be in the same spot, albeit it's going to be inverted, okay? Now, if I put the object here, the image is going to move away now on this side. It's all matter of this equation, that's all. It's all just working this equation. Okay, I'm sorry, 1 over f. Okay, so if you put the condition, s is greater than basically f, but less than 2f, and you invert the equation, 1 over s is less than 1 over f, but greater than 1 over 2f. And basically, if you solve for the equation, namely 1 over s prime, 1 over s prime is equal to 1 over f minus 1 over s. So if I subtract, if I change the sign, multiply by a negative in here, everything will change direction again. And if I add to it 1 over f, this will become 0. Obviously, it has to be 0, positive. This will become 1 over s prime. And this will become 1 over f minus 1 over 2f. And this is actually, if you calculate the algebra, this is 1 over 2f. In other words, s prime, if you invert everything again, is going to be, so since 1 over 2f is greater than 1 over s prime, s prime should be less than 2f, okay? But greater than 0, okay? So that's basically the algebra that I'm trying to work in here, okay? Did I do it right? When you invert, actually, when you invert the direction of the, I'm sorry, the direction of the, so it was less than 1 over 2f, so the direction becomes greater. So if the object was in here, the image is going to be more than 2f, okay? And you can take practical numbers to see that that works. Now, if the object sits on the focal point here, if s is exactly f, that means 1 over s prime plus 1 over f is equal to 1 over f. Cancel this on that side. That means 1 over s prime is equal to 0. That means s prime is equal to infinity or goes to infinity. That means that if I put the object right here on the focal point, the image is at the other side of the universe. It's at infinity. As a matter of fact, it disappears. When we do this lab, you're moving the object actually, and as you move it closer and closer until it gets right on the focal point, then the image disappears. And guess what? It starts to appear on the other side. Because if you move closer than 1f, if you are here, if you put the object in here, the image will become on the other side, become virtual. Okay? So if you do this one in here, and there is a mirror in here, the image becomes in here, and actually it's going to be upright instead of inverted, and it's going to be magnified, and it's going to be virtual. So if S is less than F, then in this case, the image will be on this side. Okay. This is basically just reworking this equation that we have found. Just the same equation again and again and again and again, and look at it, how S and F are related. Now, just a word of caution, and I already mentioned it, for the concave mirror, convex mirror, it's always virtual. Whereas in a concave mirror, like the one that I was talking about in here, this is a concave mirror. For a concave mirror, the image can be virtual or real. The image can be upright or inverted. The image can be magnified or basically smaller in size, depending on these things. Let's define the magnification now, because it's very important that we define it here. The magnification, by definition, M is equal to minus S prime over S, okay? So this is the magnification. If the magnification is negative, that means it's actually real. If the magnification is positive, that means the image is virtual. So again, you can define these things this way. So, and now to go back into the issue that we started with, for example, to go back into this example that we have in here, the position of the object, 75 centimeters, the position of the mirror is 37.5. So if I do this one, it's going to be negative 37.5 centimeter divided by 75 centimeters. If you stick to the same units in terms of distance, and it's a good thing to not to convert to meters. This is a problem in optics. It's a good idea to stick with the so how much magnification in here? Negative 0.5. So this is a negative 0.5. So it's clearly negative, and it shrunk by a factor of half, basically the image. Obviously, if I put it in a different point, the magnification will be different. Let's say, for example, since this is 25 centimeters, let's put the image in here, okay? Let's put it, for example, at 10 centimeters and see what happens, okay? To see if that analogy would work or not. So what we know now, the object's position is 10 centimeters, and the focal point is 25 centimeters. So let's calculate S prime. It's going to be negative, okay? So 1 over S prime plus 1 over 10 is equal to 1 over 25. Don't need to convert anything. Keep everything in centimeters, and the answer is going to be in centimeters. So it's going to be 1 over 25 minus 1 over 10. The common denominator is what? 50. This one needs to be multiplied by 2, and this one is needed to multiply by 5. So it's going to be negative 3 over 50. As I was saying, the magnification, the image is virtual at this point because it's on the other side of the mirror. It's a negative number. Remember, S prime was positive if we had it on this side. Now it turns out to be negative, so it's on the other side of the mirror. So the position of the image, actually, S prime is the invert of that number, so it's negative 50 over 3 centimeters. Negative over 3 is what? Do the math, okay? So that is basically the image. Now, if I want to find the magnification, in this case, it's going to be minus, by definition, S prime over S, and it's going to be minus times minus 50 over 3 divided by S, and S was 10 centimeters, if you guys remember, okay? Obviously, the negative and the negative cancel, becomes positive. The 10 and the 0 cancel, and I'm left with a positive 5 over 3, or 1.67. So again, it's magnified. It's increased in size, and it's upright because the magnification is positive. And it's virtual because the magnification is positive actually too. So it's virtual in this case. And the size has increased by 1.67, okay, from what it was before. So it was amplified. So again, I just took the same example and put the object instead of at 75 centimeters, I brought it closer to the mirror, about 10 centimeters. Remember that the mirror focal point is still 25 centimeters. So again, this is still how we're finding the image and we're deciding on its size and all of that. In terms of size, by convention, the object is always positive because you put the object in front of the mirror, unless it's an image that is formed from previously, okay? Because you can compound different mirrors together. You can take this mirror, another mirror, and probably also a lens that we didn't talk about, and combine them together. And now an object image from a real object, should I say? An image from a real object. So you have an object sitting in front of a device, forming an image. That image becomes an object for the next device. That can form another image that can become another. So this is how you compound basically instruments. That's how telescopes actually work, because they have different mirrors. They have the objective mirror and they have the primary objective mirror. Depending on the telescope, in this case, it's reflective of refractive. And then you have the eyepiece, which is another mirror in there, or another actually lens in there. Okay, so that is basically how these things are working. Note that the units for the magnification are dimensionless. Okay, so this is in a nutshell what's going on with the law of reflection. Let's talk about the law of refraction. So this is what we're saying now. We're taking two different media. Okay. So we have a medium in here of index of refraction NA, and we have a medium in here of index of refraction NB. And for the sake of argument, we're going to take NB greater than NA. Okay. This is where the object is going to be sitting. Position S again. And this is where the image is going to be forming S prime in here. So what I'm trying to say in here is the following. As the ray goes through this point in here, because this is the normal to the lens in this case, or mirror in this case, okay? But it uses the refraction now. This one, because it's on the normal, it's going to go straight throughout the normal, because NA sine of 0 degrees is equal to NB sine of 0 degrees. So in this case, this angle must be also 0. This is the normal. However, a ray that goes this way and hit the interface in here is going to refract. So if this is the normal, so I'm going to draw the center somewhere of the curvature C in here, okay? So this is the radius R. This is the radius R, okay? So then this is the normal now. So a ray that goes in here must converge this way. So in other words, this is the angle of incidence and this is the angle of refraction. And this is how my ray is formed now. So this is my theta A here, and this is my theta B. Okay? And this is what the image is formed now. Okay? So if I look at my geometry now, I have to be very careful in here. So I'm going to call angles in here, similar to what I did earlier. I'm going to call this angle alpha. I'm going to call this angle beta. And I'm going to call this angle phi. Okay. I know from the get-go that this angle and that angle, NA sine of theta A is equal to NB sine of theta B. This is the law of refraction. This is what we saw from the previous chapter. Okay. Obviously, for the one that is going straight through the axis, it's still true for it, except that the angle of incidence is 0 degrees. So the angle of refraction must be also 0 degrees. So that is going to form in that. So now I need to find a condition on my S and S prime, now similar to the previous one. So what I'm going to say in here is that in this triangle, look at this one. This angle plus this guy, so I'm going to look at this angle only, okay? We're going to call this point P in here. So from where the object is to P to where the center of is, it forms a triangle. The sum of theta A plus this angle is 180 degrees. The sum of phi plus alpha also is 180 degrees. So theta A must be the sum of these two angles, phi and alpha. So theta A must be equal to alpha plus phi, okay? Also, from this triangle also, that is formed from where the object is, where the image is, S prime, where the center also is, and where the point P is, this phi plus this angle is 180 degrees, and this one also plus this 2 is also 180 degrees. It's clear then phi is the sum of beta plus theta B. Phi is theta B plus beta. Okay. I'm going to use the small angle approximation. This is similar to the approximation that we did earlier for x squared to be basically negligible in front of 2rx, okay? Or x is very, very small in front of 2r. So in other words, the small angle approximation dictate that theta A and theta is approximately its sine of theta A, which is approximately also tangent of theta A. Also, theta B satisfies the same condition, sine of theta B, which is roughly tangent of theta B. Okay? If I come back to this expression, basically, I'm going to look at these triangles now. So the projection of point P on here, I'm going to take this distance from here. Again, we're going to use the approximation that delta squared is negligible. As a matter of fact, delta itself is going to be negligible in front of R. The same approximation that we use. Remember that we said that X is very, very small in front of 2R, which is R actually 2 in the order of magnitude. So delta actually is going to be the same thing. So this distance and here from here to here is of the order of the magnitude of X, okay? So this is your X distance in here. And so this distance is actually S plus X, and this distance is going to be R minus X, okay? So I'm going to look at the tangent of phi and the tangent of alpha, and so this distance, I'm going to call it Y actually. So it's going to be clearly Y over this whole distance, and this is going to be Y over that distance, okay? So that is from this right angle triangle, then I'm going to find that and sub in the values. So let's do some work in here. So from this triangle, we know that tangent of alpha is equal to Y over S plus X. Tangent of alpha is Y over S plus X. And tangent of beta, did I call it beta? I'm sorry, phi. I have to be careful with my angles now. Tangent of, no, I'm sorry, tangent of beta, I'm right. Tangent of beta, not tangent of phi, is equal to also S prime minus X. But I have, of course, the numerator is the same thing. So it's just the opposite, which is H over the same thing. So Y over S prime minus X, okay? Obviously, I'm going to take the limit when these two are negligible in front of S and S prime. And I'm going to use this approximation in here. So we're going to say theta A, which is equal from this equation, NA times sine of theta A, which is theta A, roughly, is equal to NB times sine of theta B, which is theta B. So I'm going to sub the value of theta A here, and I'm going to find a condition on alpha and beta from the second equation. Okay, so the first equation says that Theta A is just NB over NA times theta B. So it's NB over NA times theta B, that is theta A from this equation, equals to alpha plus phi. And phi is theta B plus beta. Phi is theta B plus beta. Now move theta B to the other side, and we have a condition now on this angle. So we have NB over NA minus 1 theta B is equal to alpha plus beta. Or if you wish, multiply everywhere by NA, and you will have NB minus NA times theta B is equal to NA times alpha plus beta. Now, I'm going to use this condition now for the tangent of alpha, again, approximately equals to alpha. So from here, we're going to get alpha, again, using the same approximation, is going to be y over s, and beta is going to be same y over s prime minus x. And what else do we need in here? I need hold on. We have theta A, we have theta B. So we're going to express it in terms of theta A, and theta A is expressed in terms of alpha. You know what? We are out of time right now. So what I'm going to do is, I'm going to finish the derivation later on today. We're meeting anyway. And hold on, let me stop sharing the screen in here. Okay, very good. So we're going to finish the derivation. We're going to find the condition similar to what we found earlier, okay? The radius r. Yeah, actually, I'm sorry. We can use the condition for the angle phi, which is also the tangent of phi equals to y over r, okay? R minus x, and x is negligible in front of that. And that is going to give me the other condition that we will need, because we need to get rid of alpha, and one of them is already alpha is y over s. The other one is beta is equal to y over s prime minus x. And we need another condition. And the other condition, we can find it from phi itself. The tangent of phi from the geometry, if you go back into it, let me share the screen so that you can see what I'm talking about here. The tangent of phi from here is equal to y over r, okay? Tangent of phi is y over r. So basically now we're going to have this expression in terms of phi here, and in terms of theta b and beta, and theta b we have it already, and beta we can find it in here, and theta b also has to do with alpha, so we can get rid of the alpha because we need to get rid of both of them. So we'll have theta b now in terms of y and s and s prime. I'm sorry, I should have neglected this term in here in the because remember, we're taking x to be very small. So what we're saying in here is we have, so what we will find in here is theta b is equal to na times this difference, of course, alpha minus or plus beta. And then we have another equation that involves also phi and theta b. Although we used that equation before to get into this equation, but it's still, we have two independent equations. So now once we find phi, which is just the ratio of y over r, we can get rid of all of them, and we will find a condition that involves y over r, y over s, and y over s prime. So y cancels throughout, and you only be left with a condition that is going to be basically involving just s and s prime, so it's going to be na over s plus nb over s prime is equal to na or mb minus na over r. This is the other equation that you will need, okay? And you can express it for the case of refraction this way. So we're going to find that one because y is going to cancel throughout both sides. You're going to find this condition on how the image is formed in this case, okay? you can call a modified version of S, modified if you wish, as being just the old S over NA. In other words, this is your optical path in any region where light is traveling with a different speed other than C. So you can define it that way. And again, so S prime modified would be simply equal to S prime over NB, where S prime is in vacuum. Now, but this is traveling with less than the speed of light by this factor. So, and then you define the focal point, F, as simply being R over NB minus NA. And you plug into the equation, this becomes the new version of the same thing that we did before. 1 over, this is modified though, plus 1 over S, which is modified by the optical path. And this is equal to this version of F, the focal point for this device. So it's still identical to the first equation if you do these modifications. You're concerned only with the optical path, not with the actual path, not with the one that is you're looking at, the optical path. Light takes this much time to go from one point to the other because it's traveling slower, okay, from the other one. So that is really the equation that we're getting into. And the missing link was this condition on phi, tangent of phi being y over r, okay? You really don't care about derivation, you really care about the homework and all of the problems. This is still the main equation. This is gonna be true also for lenses too. It's gonna be true everywhere, okay? So, we're not done with this chapter, unfortunately, so we still have stuff to do with it. I'm gonna talk a little bit about the lab. Do you guys have time? Can you hang around for about 5-10 minutes? Because the lab is kind of short, honestly, in terms of concepts, but it's long in terms of work. Or should we have like a 10-minute discussion later on at 2 o'clock before you guys do the lab? You tell me. I already went beyond the time now. Should we meet at 2 o'clock to do the lab? Yes? Okay, so at 2 o'clock then we're going to meet to discuss the lab. Again, like I said, the intro is gonna be super brief because once you understand how things work, you should be fine. You can do it. And I'll see you later on at 2 o'clock. So I'm gonna stop the recording.